Imagine a universe that has existed forever, a cosmos without beginning or end, an infinite expanse of time stretching endlessly into the past and future, a truly eternal realm where existence knows no bounds. Picture eons upon eons unfolding, with galaxies swirling and stars igniting across the vast canvas of space. But this poetic idea, this vision of an everlasting universe, hides a troubling contradiction, a paradox that challenges our fundamental understanding of reality. It's a conundrum known as the heat-death paradox. If the universe has been around for an infinite amount of time, stretching back into an immeasurable past, then a question arises that strikes at the heart of cosmology. Why hasn't it run out of steam? Why isn't the universe a cold, desolate wasteland, devoid of energy and activity? Why is anything still happening? Why are stars still being born, galaxies still colliding, and complex structures still forming across the cosmos? According to the laws of physics, especially the principles of thermodynamics, which govern the flow of energy and the increase of entropy, every system should eventually reach equilibrium, a state of maximum entropy where energy is evenly distributed and no further work can be done, a state where nothing interesting can ever happen again. A uniform, featureless void where all temperature differences have vanished. This is called heat death. A final static state where all energy is spread out uniformly, and the cosmos is utterly still, silent, and unchanging. A truly dead universe. Yet when we look up, when we gaze out into the night sky, we see a vibrant, dynamic universe, a cosmos teeming with activity and energy, full of stars shining brightly across vast distances, galaxies swirling in majestic formations, colliding and merging in cosmic dances, and life flourishing on at least one planet and potentially countless others. The paradox is clear, a stark contradiction between theory and observation. If the universe were truly eternal, if it had existed forever, it should have reached heat death long ago, becoming a cold, lifeless void. So either the laws of thermodynamics, which we hold to be fundamental, don't apply to the universe as a whole, or the universe hasn't existed forever, implying a beginning, a moment of creation. This puzzle forced scientists to reconsider, to reevaluate their assumptions about the cosmos, the very nature of time and the origin of everything we see, from the smallest particles to the largest structures in the universe. The heat-death paradox became a signpost, a crucial piece of evidence pointing toward a universe with a beginning, a finite age. It's not just a minor inconsistency, a small detail to be brushed aside. It's a deep fissure in our understanding of reality, a fundamental challenge to our cosmological models. And it all starts with a simple question, a seemingly straightforward inquiry: why isn't the universe dead yet? Why is it still so full of life, energy, and activity? The heat-death paradox emerged in the 19th century, an era of steam engines and scientific revolution. Scientists like Lord Kelvin and Rudolf Clausius were formulating the laws of thermodynamics, which describe how energy spreads and becomes less useful. Kelvin realized that if the universe obeyed these laws and was infinitely old, it should have wound down to heat death by now. But the universe is clearly not in that state. Their logic was simple: if the universe were eternal, it would be in equilibrium. Since it isn't, it must have had a beginning. This was a radical idea, challenging centuries of belief in an eternal cosmos. The paradox forced scientists to confront the possibility of a universe with a finite past. It was a turning point in our understanding of existence. Let's break down the heat-death paradox. It sounds intimidating, but the core concept is surprisingly simple. We can understand it better with a simple analogy. Imagine finding a steaming hot cup of coffee sitting on a kitchen counter. The aroma fills the air and you can see the heat rising from its surface. You instinctively know it hasn't been sitting there forever. If it had, it would have gradually cooled down, eventually reaching room temperature. The heat would have dissipated into the surrounding environment. The very existence of that hot coffee radiating its warmth proves that it was poured relatively recently. Someone must have brewed it and placed it there not too long ago. Now let's scale this up. Think of stars as being like that hot coffee, constantly radiating energy in the form of light and heat into the vast, cold expanse of the universe. They are cosmic furnaces, burning through their fuel and emitting energy. Now, imagine if the universe were infinitely old, stretching back into an endless past. In that scenario, all the stars and galaxies should have, by now, exhausted their fuel and cooled down completely, reaching a state of thermal equilibrium. The entire universe would have reached a uniform, chilly temperature, a state of maximum entropy, where no further energy transfer is possible. But when we look out into the cosmos, we see that our universe is anything but uniform. It's full of stark contrasts. We observe incredibly hot stars blazing with nuclear fusion, alongside extremely cold gas clouds, the birthplaces of new stars, and galaxies violently colliding and merging with each other. This dynamic and ever-changing state tells us that the universe hasn't been sitting here in a state of equilibrium for an infinite amount of time. Just like the hot coffee, the universe, with all its vibrant activity, must have a finite age. The heat-death paradox uses this simple but powerful logic to argue that the cosmos must have had a beginning, a point of origin. Our universe is far from being in a state of equilibrium. It's a dynamic and evolving system, constantly changing and transforming, and the evidence supporting this is all around us, visible through our telescopes and in the data we collect from across the cosmos. The paradox, therefore, isn't a problem, but rather a valuable clue that helps us piece together the universe's true history and understand its origins. It's a cosmic detective story, written in the light of distant stars and the echoes of the Big Bang, waiting for us to decipher its secrets. To understand the heat-death paradox, we need to delve into a concept that governs the very fabric of our universe. It's a principle that dictates the flow of energy and the inevitable progression of all things. Meet its central character, entropy. This seemingly simple term holds the key to unlocking one of the universe's greatest mysteries. Entropy measures disorder, or more precisely, the number of possible arrangements of a system. The higher the entropy, the more disordered the system. The second law of thermodynamics, a cornerstone of physics, states that entropy in an isolated system always increases. This is not just a suggestion but a fundamental law that governs everything from the smallest atom to the largest galaxy. It's a one-way street, order to disorder. The universe seems to have a natural inclination towards chaos. Think of your bedroom. It takes effort to keep it tidy, a constant input of energy to fight against the natural increase in entropy. But left alone, it gets messy. It's the universe's way of reminding you of the second law. That's entropy in action, a relentless force pushing towards disarray. Or imagine a box divided between hot and cold gas. This is a classic example used to illustrate entropy. Remove the divider and the gases mix, driven by the tendency to maximize disorder. Reaching a uniform temperature, maximum entropy. The system has reached its most probable state. The universe is the ultimate isolated system, the largest container we know of, so its entropy must always increase. This has profound implications for the fate of the cosmos. Every star, a furnace converting hydrogen to helium. Every reaction, from the smallest chemical process to the largest supernova, adds to this cosmic march toward disorder. It's a relentless, unstoppable process. The universe began in a low entropy state, a highly ordered and compact form, and has been unwinding ever since, expanding and cooling, spreading its energy across an ever-increasing volume. If this process had been going on forever, if the universe were infinitely old, the universe would already be at maximum entropy, heat death. A state of complete equilibrium where no further work can be done. But it isn't. The universe is still teeming with activity, with stars being born and galaxies colliding. The paradox points out this contradiction, this apparent discrepancy between theory and observation. Entropy's relentless increase is the engine behind the puzzle, the driving force that leads to the prediction of heat death. The universe's ongoing activity is the evidence, the undeniable proof that something is amiss with our understanding. The second law of thermodynamics is often called time's arrow. It distinguishes past from future. Most physical laws work the same forwards and backwards, but not this one. Scrambled eggs don't unscramble, broken glass doesn't reassemble. The law says heat always flows from hot to cold, never the reverse. This flow powers everything from engines to stars, but with each transfer some energy becomes less useful. The sun, for example, radiates energy into space, increasing entropy. Eventually all stars will burn out and the universe will cool. An eternal universe contradicts this law. The second law paints a picture of a universe with a beginning and an end, a journey from order to disorder. Kelvin and others realized you can't have both an eternal universe and the second law. One idea had to give way. The paradox forced a choice. The night sky is proof the universe isn't in heat death. We see hot stars against cold, dark space, a stark contrast. If the universe were infinitely old, this temperature difference would have vanished. Yet, stars still shine, and new ones are forming in stellar nurseries. The process of star formation shows the universe is still evolving. In a heat-dead universe, no new stars could form. The cosmic factory is still running. The evidence is everywhere. The universe is not infinitely old. It's in a middle chapter, still full of energy and potential. The cosmic clock was wound up at a specific moment and is now slowly winding down. The heat-death paradox haunted scientists until the 20th century, when the Big Bang theory arrived. The Big Bang gave the universe a finite age, about 13.8 billion years. This solves the paradox. There hasn't been enough time for heat death. The universe began in a hot, dense, low-entropy state, and has been expanding and increasing in entropy ever since. The cosmic microwave background is the afterglow of the Big Bang, a relic from when the universe was young. Tiny fluctuations in the CMB seeded all cosmic structure. Modern cosmology weaves the paradox into a complete narrative. The universe had a beginning, and entropy has been rising ever since. The process is far from complete, which is why the universe is still vibrant. The paradox is now a powerful piece of evidence for a universe with a finite past. It's no longer a contradiction, but a cornerstone of modern cosmology. The heat-death paradox isn't alone. Olber's paradox also challenged the idea of an eternal universe. Olbers asked, if the universe is infinite and eternal, why is the night sky dark? In such a universe, every line of sight should end on a star, making the sky blazing bright. But the night sky is mostly dark. Dust can't explain it. Over infinite time, dust would glow too. The Big Bang solves this. The universe is only 13.8 billion years old, so we can only see light from within our cosmic horizon. The expansion of the universe also stretches and dims distant starlight. Both paradoxes point to the same conclusion. The universe is not eternal and static, but dynamic, with a definite beginning. They are cosmic clues, solved by the same revolutionary idea. The night sky's darkness and the universe's activity both reveal its true age. Today, the heat-death paradox is considered solved thanks to the Big Bang, but it remains a brilliant example of scientific reasoning and the power of theoretical physics. The paradox forced scientists to consider a cosmic beginning long before we had direct evidence. It's a historical signpost that pointed science in the right direction. The concept of heat death now describes a possible future for the universe. Entropy is still increasing, and the universe is still winding down. In the far future, all stars will burn out, black holes will evaporate, and the universe will become a cold, empty void. The paradox connects the birth of thermodynamics to the frontiers of cosmology. It started with a simple question: why isn't the universe dead yet? And led to profound answers about our origins and fate. The heat-death paradox remains a bridge between past mysteries and future discoveries.